As we wind up now, Chapter 2, Topic 2.8, Modeling Variations. These are the objectives. There's basically four types: direct variation, inverse, combined, and joint. And we'll give examples of each type. Now, when we do direct variations, as you look at the general formula of this, you'll notice it's in the form of y equals mx plus b, which is sort of a straight line from an earlier lesson. And where m in direct variation is listed as k, this is the constant of variation, and then x is some value. Okay, so let's just read this here. Where k is the non-zero constant, we say that y varies directly as to x, or y is directly proportional to x. And k is the constant of variation, or the constant of proportionality. Kind of a little wordy. All right, let's go on. Now, there is a protocol for solving it. I'll go through this with you, but if you want to pause and read it, that would be fine. Okay, let's look at an example now. Again, this is example 1. The number of gallons of water, W, used when taking a shower varies directly as the time, T in minutes. In the shower, a shower lasting 5 minutes uses 30 gallons of water. How much water is used if the shower lasting 11 minutes? Okay, so we'll do it by step. Step 1, this is an equation of direct variation, which is going to be y equals kx. This is a general form. But now what we're going to do is replace the y with water used. K is our constant of variation, and we're going to replace the x with the t, which is time. So what information do we know from this? Well, 30 gallons is the amount of water. We don't know our K value, but we know the time was 5 minutes. So that's step 1. Now, step 2 is we have to find what K is. So we solve this equation for K. Divide both sides by 5 here. And we get K then equals 6. Continuing now, we write and substitute what we know for our K value in the original equation. So W equals, our new value of K now is 6 T. So now we show the relationship to our original. How much water will be used if a shower is lasting 11 minutes? So this is going to be 6 times our time now, which is 11, and that's going to use, wow, 66 gallons of water. And we see it here. Okay, so kind of straightforward, and it does relate to slope-intercept. Now, another form of direct variation is one in which we're raising some value to a power, that it will be squared or cubed. So we say that y is directly proportional to the nth power of our variable x. All right, let's look at an example. Example 2 says the weight of a great white shark varies directly as to the cube of its length. Okay, so our standard formula will be the weight of a shark is equal to some constant of variation, but now it's to the length that is going to be cubed. So substituting into the equation, we got the 2025 equals k, 15 to the third power. Now they've worked that out for us. 15 to the third power is 3,375. We're going to divide both sides by that, and then we solve for k, and k is 0.6. So what do we do now? Well, we'll clear this up, and we'll go to the next slide, where we substitute into our original formula, w, our new value of k, and then we'll solve it. So w equals 0.6. Now our new length of this shark's a big one, 25, the quantity cubed. All right, the next slide is going to show us what happens here. And let's clear it up. And we get 15,625 when we cube 25, multiply it by 0.6, and it ends up being 9,375. And historically, that was the weight of the big white shark in Jaws that some of you may have seen. All right, let's go on. Now, for inverse variation, that basic formula is what you see here. Y equals k over x. And another way this is sometimes represented, it's in a fraction equals a fraction. We can just cross multiply, and it gives us then xy equals k. So k is the product of x and y, whatever those values are. Now, where k is a non-zero constant, we say that y varies inversely, as x or y is inversely proportional to x. K is still called the constant of variation. All right, let's see an example. So starting off, we see the length of a violin string, and this is example 3, varies inversely as the frequency of its vibrations. A violin string, 8 inches, this is the length here. We don't know our K. Vibrates with a frequency of 640. So K is going to equal, again, this is over 1. We're just going to cross multiply. 8 times 640 will be our K value. And we'll see that on the next slide. So our K value then is going to be 5,120. So we're now going to write the formula for inverse variation. L equals 5120 divided by X. Now, what will be the frequency if the string is 10 inches? So we're going to put a 10 here. And I'll just erase this. And actually all it does is it drops off this 10, and it's going to be 512. So some easy examples, I believe. Let's see what it shows here. Clear that up. And 512. Okay. Now here another type is combined variation, where we have direct variation and perhaps inverse variation occurring at the same time. Let's look at an example of this. Example 4, the number of minutes needed to solve an exercise set of variation problems vary directly as the number of problems and inversely as the number of people working to solve the problems. If it takes 4 people 32 minutes to solve 16 problems, how many minutes will it take 8 people to solve 24 problems? So again, M will be the number of minutes, N the number of problems, and P the number of people. But we still need to find what our constant of variation is. So in our next slide, we'll substitute, and we can just use this work. So our M is 32, and this, remember, is times here. So notice what we could do here also. We could do a little cross-canceling. 4 goes into there once, 4 goes into there 4 times. So we got 4K equals 32. We're going to now divide both sides by 4, and we get K equals 8. So our problem then in the future will be M equals 8 N over P. So in our next slide, we see our basic formula. We have the constant of variation. How many problems? 24. How many people? 8. And notice what happens here. The 8s will just cancel out nicely. So it will take 24 minutes to solve 24 problems. All right, going on now to our last type of variation, which is joint variation, where you could have direct variation and then some other things varies jointly as X and Z. So let's take a look at a problem. The volume of a cone, V, varies jointly as its height and the square of its radius. All right, so we see it there. This is actually the volume formula of a cone. What we don't know is what is the constant of variation. So they're giving us values. The radius is 6. Remember, we're going to have to square that radius. The height, the h, is 10. And the volume is 120 pi cubic feet. Okay, so let's go to our second slide. We're going to substitute into it our 120 pi k, and we can put parentheses around these in a sense. So this becomes 36 times 10 is 360K. So dividing this by 360, both sides, this goes into there once, this goes into there 3 times. So you end up with, in a sense, 1 pi over 3. You don't write the 1. So pi over 3 is our K value. So we're now going to put volume equals pi over 3 h r squared. And that'll be our next calculation in the next slide, which is what we put here already. It's this slide. Okay. So now we have h is going to be, our new is 2 feet, which is 2 right there. I don't know where those little boxes are coming from. But our radius now is 12 that we're going to square. So this is 144 times 2 is 288 divided by 3 is 96 pi is our answer. So we've seen examples of all 4 types of variation: direct, inverse, combined, and joint. All right.